So our next presentation is a joint presentation. The first student is going to be Lina Espinosa. Lina is a PhD student at North Carolina State University, and she's working with the seismic behavior of columns under low temperatures with high-strain reinforcing steel. This presentation is also going to include part of my research in the RoundHouse stress-strain curve. And I'm a master's student also at North Carolina State University working with grade 80 mechanical splices. Well, let's all welcome Lina to start the presentation.
Thank you, Malu, for the introduction. So for this presentation, we're going to talk about the manufacturing process impact on the seismic behavior of high-strength reinforcing steel. I'm going to start with an introduction, then I'm going to focus on that impact that we have seen from the seismic performance. And then we're going to talk about a preliminary study on how the RoundHouse nature of the stress-strain curve can affect the seismic prediction of reinforced concrete columns, and we're going to finalize with a summary. So how many of you have considered the manufacturing process when selected your reinforcing steel? 1, 2. Okay, but not too many hands, right? This is a question that we don't typically ask, but I hope that by the end of the presentation we can start thinking about it a little bit more, right? So what we are defining as high-strength reinforcing steel is reinforcing steel with yielding strength of 80 psi or above. Right now in the United States we have two main manufacturing processes. The first one is microalloying, where small additions of alloy are included into the steel make to increase the strength. These alloys help preventing the grain dislocation, delaying the onset of buckling. The onset of yielding. We also have the quench-off temper. That is a thermomechanical process. This process, the surface of the bar are rapidly cooled with spray water, and then the hot core soft temper the bar. And this results in a cross section that has different material properties across the section, and this is what contributes to the higher strength. So when we talk about the seismic behavior, the reinforcing steel plays an important role on the column performance limit state. So the typical failure mode that we have for reinforced concrete columns is bar buckling following by bar fracture. The damage control limit state of bar buckling following by bar fracture, the bending strength capacity of the reinforcing steel plays an important role in this limit state. And I'm going to talk about some parameters that we have identified that played a role in this bending strength capacity. So usually to evaluate the seismic performance of reinforced concrete columns, we conducted quasi-static lateral loading, where cycles of loading, pushing, and pulling are applied into a column in increasing ductility levels. From previous research comparing grade 60 steel with grade 80 steel, it was observed that the main difference occurred in the post-buckling behavior. So once the reinforcing steel buckle, the columns reinforced with grade 60 steel, they had the ability to sustain more cycles of loading, contrary to what happened to the grade 80 steel. To evaluate this further, Leo Barkley and Dr. Mervyn Kowalski, they developed a material level test that replicate the loading condition of the column, the reinforcing steel in a column. So in this test, first, the bars are subjected to a certain level of buckling that is represented by the level of bending strain. And then the bar is pulled until failure, and we observe what is the type of failure that we obtain under a certain amount of buckling applied. Multiple bars are subjected to different levels of buckling, and what we look is for that amount of bending strain that results in a change in the failure mode from ductile to brittle. This is what we call the critical bending strain. And this parameter is mainly influenced by stress concentrations that occur at the base of the ribs at the section of the maximum curvature in the bar. So what you can see in this chart is every point represents a bar that was subjected to a certain amount of bending and strain. So bending and strain is in the horizontal axis, and then the vertical axis represent what was the elongation capacity of those bars. For the bars that has a higher elongation capacity, we had a ductile failure, but for those that the elongation capacity was near zero was because it was a very brittle failure where sometimes even the bar were still in the vocal shape. What we look in this specific test is where does that transition from ductile to brittle occur. And what was observed comparing grade 60 steel with grade 80 steel is that grade 60 steel had a larger bending strain capacity that also correlates well with what was observed the global behavior of the reinforced concrete column, given the larger displacement capacity. So this test has been used to evaluate more parameters that affect that critical bending strain, and one of those was also the geometry of the bars, of the rib radii. And the result for this one, here I'm putting a more extreme condition, let's say, because in this chart we're comparing rib bars with smooth bars. So the ribs were removed just to see what was that effect of the stress concentrations. And you can see that there is a big difference between the ribbed and smooth bars. And lastly, another factor that played a role was the manufacturing process. For the micro-loin bars, there is a typical way of behavior where you can see a very defined transition from ductile to brittle. However, this transition occurs smoothly when we use quench soft tempered bars, and they tend to have a larger critical bending strain capacity. So far, research have told us that the strength of the steel, the rib radii, and the manufacturing process play a role into the bending strain capacity of the reinforcing steel. However, these results have been getting from quasi-static lateral loading and also room temperature conditions. And this leads us to where is our research right now? What else do we need to take a look at, right? So two of the parameters that we are addressing right now is first low temperature, and the other one is high strain rates. Earthquakes are not quasi-static. Earthquake has very wide variety of strain rates. So I'm going to start talking about the low temperature and why we're doing this. So we know already that the combinations of low temperatures and stress concentrations can be catastrophic. And there are multiple regions around the world that are subjected to these combined actions of earthquakes and severe cold weather, such as the case of Alaska, where we can have temperatures of -40 sustained temperatures. And this makes these particular conditions special to analyze, to be able to incorporate high-strength reinforcing steel under these conditions. So right now, high-strength reinforcing steel is not allowed to be used in members expected to form plastic hinge in Alaska due to the lack of understanding at this point. There are some temperature-dependent requirements on grade 60 steel that includes expected material properties, overstrength factors, and also reduction in plastic hinge length. And for my research specifically, we're looking at this combination: high-strength reinforcing steel, a material that is more susceptible to stress concentrations; low temperature, a condition that aggravates the effect of stress concentrations; and earthquakes. Well, we need a lot of deformation capacity, and I mentioned already how much these stress concentrations can affect that displacement capacity. So to address this problem, we started with a material level evaluation. I conducted buccal bar tension test and monotonic tension test, evaluating the different manufacturing processes. For this research, I'm just going to focus on the results that we obtained from buccal bar tension test in the manufacturing processes, but we're also seeing different steel grades using grade 100 and grade 80. And we're conducting this test from room temperature to minus 40 Fahrenheit. What we observed from the buccal bar tension test is that for the microloid, we were still achieving that typical abrupt transition in the failure mode. And there was an impact of the temperature on the critical bending strain. So at room temperature, critical bending strain was ranging from 17 to 19%, and at low temperature, it decreases to 14 to 16%. For the case of the quench of temper, we didn't observe this clear behavior. Differences in behavior, it looked very similar to the room temperature conditions. And now the next step of my research, we're working on doing quasi-static lateral loading at low temperatures. So we have an environmental chamber where we will place our column. It has to be in a horizontal position because of the geometric limitations. And we're going to evaluate and to be able to correlate those results that we obtain from the material level to the global behavior. This is a picture of how my experimental setup looks like. We did already 2 of the room temperature tests. I still need to process the data, and we're working on the low temperature ones. With this research, we want to develop design recommendations to incorporate high strength reinforcing steel in cold seismic regions. And that it's in terms of what's going on right now with low temperatures and the manufactured effect. The other portion that is being studied in this moment is the effect of strain rates. So as I mentioned, we are evaluating the seismic performance in a quasi-static way, but this doesn't represent the reality where we can have a wide variety of stress rates. We know that the stress rate can affect the strength of the steel in monotonic tensile loading. However, we don't know what is the effect of that strain rate on the stress concentrations and how the manufacturing process can impact this effect. One student, PhD student at NC State, her name is Luisa, together with Fabi Claudine, they are working on shake table test. Lu is specifically looking at how high-strength reinforcing steel behaves under shake table test, and their research goals are to evaluate the demands, evaluate the parameters, and also validate and calibrate the strain limited states recommended. So they're doing 16 columns using different manufacturing processes to obtain the data. They're using the 3D optical measurement system that allows them to have a 3D position of all the sensors to obtain displacement and strains of the longitudinal steel bars. Up to this point, they already did 4 tests. This is a picture of one of their tests that went all the way to collapse. And moving forward with this research, what they're looking at is they want to verify all of those limited states that were defined using quasi-static and calibrated with the results at high strain rates. So closing, the impact on the manufacturing process on the seismic behavior, yes, it's important to look what is that manufacturing process because it affects the seismic performance of reinforced concrete columns. And with this, I'm just going to give space to Malu to continue with this presentation. Thank you.
So Lina already talked about the evaluation of, of concrete columns and the importance that we see on high-strain reinforcing steel. and how that plays a significant role on structural performance, right? So specifically talking about seismic design and performance-based design, we need defined limit states in order to predict structural behavior, because we need to define our behavior when we start the design process. So there are a lot of design recommendations, such as the plastic hinge length method, that we need two main parameters to describe our materials. I'm pretty sure we're all familiar with ultimate tensile strength and yield strength. That's how we characterize our materials and how we include our material characteristics into the design process. So for grade 80, ASTM A706 grade 80 steel reinforcement, a study was conducted in 2016 by Overby et al., and they looked into hundreds of material testing bars for grade 80, and they defined what was the expected mechanical properties for this material. So they analyzed 3 different mills and 2 manufacturing processes. So he looked both into microalloy steel and QST steel. All of the tests that he did fitted well into what we call the King model for steel. And that represents a steel that has a very defined elastic region followed by a defined yield plateau and then a strain hardening curve, right? So from those tests, he recommended different model parameters that could fit into grade 80 steel reinforcement. But then a question is raised, okay, what if I'm using a longitudinal steel ratio in my column, but my stress strain curve doesn't fit into this model and doesn't fit into the parameters that were seen before? So I looked into that because I was doing a different project for mechanical splices, and while I was doing my material characterization, I noticed a significant difference between the shape of the stress strain curve for my microalloy steel and my QST steel. I must note here that this is not something that happens for every QST steel, but it was something that happened for my specimens, and as you can see, the QST steel here presented a RoundHouse characteristic curve, and that is represented by an undefined yield plateau and a curve that just is a continuous yielding curve until the point of failure. So in this case specifically, the shape of the stress strain curve was modified in order to achieve certain specifications, which is not a problem, but the consideration that we need to take here is, okay, we have this curve, and how would that affect the actual structural behavior, right? If I put that into my column, would that behave the same as the steel that was tested previously? Would the shape of the stress strain curve have an effect on my seismic behavior? So to evaluate that, I conducted a parametric study, and the 2 parameters that I changed were the actual load ratio of my columns. I did both 5% and 10% actual load, but also changed longitudinal steel ratio, increasing by 0.5% from 0.5 to 4%. And for each combination of those parameters, I did 2 moment curvature analysis, one using the King model for steel, taking the real ultimate tensile strength of the material that I was using, and using yield strength as the one calculated by the 0.2% offset method, which is the most common method for calculating yield strength right now. So I compared those results with moment curvature analysis that were performed using the complete stress strain curve. So instead of taking the tensile strength and the yield strength here, I used the full curve to calculate the moment curvature. And in total, with the combination of those parameters, that includes 32 analyses. So the graph that I'm going to show here represents 16 of those moment curvature analyses, and you can see that here the dashed lines represent the King model using the real T to Y ratios calculated per ASTM, and the non-dashed lines represent the moment curvature using the real shape of the stress strain curve, right? So the colors change based on longitudinal steel ratio, and as you can see, there is a gap in the moment demands for the King model and the real stress strain curve. And that gap increases proportionally to the increase of longitudinal steel ratio. So what that is telling us is that when we use a RoundHouse curve steel as a longitudinal steel, it doesn't behave exactly the same as if we use the model for T to Y, for example, in our design provisions. So in order to evaluate the results that I was getting, I calculated the maximum difference for each one of those combinations. And as you can see, the moment differences for the service level were a maximum of 6.6%, in the maximum value of moment at that point. And we noticed that there is a direct correlation with longitudinal steal ratio, but there is not an impact of axial load ratio in this behavior. So the second part of this study was then, okay, so how can we fix this problem? How can we address this in a simple manner? And the way that we did that is, this is an example of one combination of moment curvature analysis for the RoundHouse curve, which is the pink one, and then using T to Y in the King model, which is the blue dashed line. So we wanted to change the T to Y ratio for the dashed blue line to match the pink one. So in other words, we wanted to define a factor that would multiply T to Y to accurately predict the behavior of RoundHouse stress strain curve for lateral loading of columns. And that was the result. I did that for all of the moment curvature analysis, but I didn't want to put it all in one graph. So we noticed that on average, for us, a factor of 0.92 got us to the actual behavior with the real stress strain curve, taking into account the shape of the stress strain curve. So in conclusions, we can say that the 0.2% offset method may not fully represent the yield characteristic for reinforcing steel that doesn't have a defined yield plateau. We can also say that for design provisions such as the plastic hinge equation that rely on T to Y, it may accurately predict the behavior if we use a factorized T to Y. And for the parametric study here evaluated, we suggested a value of 0.92 as a reducing factor for T to Y. However, it is a limited set of data and more research should be considered to validate this hypothesis. So to conclude this presentation, as Lina presented before, we know that the manufacturing process plays a significant role in the seismic performance of high-strain steel reinforced concrete columns. The first issue that we see is stress concentrations. We notice that manufacturing process plays a role on stress concentrations, which is affected by low temperatures, but also by high strain rates. And the manufacturing process can also change the shape of the stress strain curve, which could affect provisions in design that rely on T to Y ratio. So my final question for you after this presentation is, should we consider manufacturing process in our design process? I'll be happy to answer any questions.